So we are in Introduction to Statistical Learning, Chapter 4, and we're on question 11. And so let me just pull the book over here. So earlier in the chapter, we are looking at different, we are finding that in a classification setting, we can convert this expression into some kind of linear expression, okay? And the example that is being looked at right here is for linear discriminant analysis, right? So when you break all of this down for linear discriminant analysis, you come up with, you get this expression right here, and then you can convert this into a simplified expression like this, where AK and BKJ are coefficients that correspond to some parts of this expression up here. And when you go to the next page, you find that AK equals all of this, and that BKJ equals all of this. Okay, so that's fine. And then it tells us that with quadratic discriminant analysis, we can do something very similar. And then we get an expression that looks like this, right? So it has an AK and a BKJ term, coefficient, but then we also have this quadratic term, which makes sense because it's quadratic discriminant analysis, okay? And so in question 11, we are tasked with taking this expression, but now assuming that it's a quadratic discriminant analysis problem, and arriving at an expression that we can convert to this. Okay, so that's what we're doing. So now this question is difficult, and it took me a while to work through it, largely because it's just a lot of linear algebra, and there's a lot of places to make mistakes. So if you're not good at linear algebra or you don't know much about it, that's fine. You can kind of walk through the derivation here, but I think what's maybe important is just simply the result that I get here, or maybe even the knowledge that we can take this expression for converted from quadratic discriminant analysis and arrive at some kind of function like this. Okay, that might be more than enough. But anyway, so I'm going to kind of step through this derivation, just kind of how I got it, but the details. One, you should look at for yourself and just kind of convince yourself of each step. But two, make sure that I have done it correctly. There's a lot of places in here to make mistakes. So there's a non-trivial chance that I have made mistakes in here. And if I did, I would very much like to know. So, okay. But anyway, so this is what we do. So we take our expression, which is just this. It's the prior probability of category K times its probability function, probability density function, and then the same for the reference class capital K. Okay, so pi k's, these are just, well, those are just going to set off to the side. Again, they're the prior probabilities, and then the fk's, the probability densities, we're assuming in this setting that they're normal distributions, and for a multivariate normal distribution, this is the expression right here, okay? So what we have is the data x minus the mean of x. So these are, well, that's a vector and that's a vector, so I subtract one from the other, and that's a vector. And then I have my covariance matrix for little k, and then my covariance matrix for big K. Now remember, the thing that distinguishes quadratic from linear discriminant analysis is that we no longer assume that all classes have the same covariance matrix. Okay. Instead, what we assume is that each category has its own covariance matrix, and that's where all of the trouble comes in here. But anyway, so this is the expression for f little k, and this is for f big K. Okay. And so now it's just trying to break this thing down, and so the first thing that I did is distribute the 1/2 sign. Well, no. So actually, the first thing I did was take the logarithm of all of this. So we take the log to an exponential, and then you just get, whatever was in the exponent, right? So now that's broken down, and then I'm simplifying and simplifying, right? So I distribute the 1/2, so on and so forth. And now eventually what happens is, probably from this step to this step, this is where you can really start to get into trouble, okay? Because all of these terms, so this whole term here, this is just one big matrix multiplication, right? Well, it's vector and matrix multiplication, but I have two vectors, one here and one here, on either side of this matrix, and so then I have to start multiplying that out and expanding that entire product here, okay? And so when you expand that out, you can, even if you're not familiar with linear algebra, you can kind of see how this is going. It's just like distributing. So I take, so I have my x, and I multiply it by my covariance matrix times the x, okay? Now normally that would be like x squared sigma because I have two x's, but when we're in the linear algebra world, we can't quite do that, and so the multiplication takes on this form where we have this transpose, and so I have to carry this x transpose sigma x, and then you keep that in the same order, okay? Or sigma inverse, I should say, okay? And so we get that term, okay? And then similarly, we would do x transpose inverse of sigma mu, okay? And then we get that term, okay? So anyway, so we just expand all of this, and we get all of this stuff here in parentheses. And then we do the same thing for this guy over here. And it expands into all of these things right here. Okay. And so now I just distribute this minus sign, and I get all of this. Okay. So so all I did was I just distributed this minus sign to everything here. Okay. And now I'm just distributing my 1/2. So here's the 1/2, and so I'm just breaking it down into discrete terms here. Okay. And I've kind of clumped these terms a little bit here. Okay. So here, everything without an x, I've kind of clumped into this parentheses. Okay. So from the expression above, the things that don't have an x, right, I've clumped here. Okay. And it's going to turn out that this is going to be part of our a coefficient, right? It's going to be this part right here. And that makes sense because notice that a has no dependence on x, okay? And then I have, let's see here, where am I? And so now I have this term right here. And so all I've done is I've clumped all of the terms that just have one x, right? Because that's going to be my linear term eventually, okay? So this just has one x, this just has one x, this just has one x, etc. And then finally I clump together all the terms that have two x's, okay? So again, if I've done that correctly, all I've done is I've just kind of rearranged the terms up here after distributing the 1/2 to get the ones with no x's, with one x, and with two x's, okay? Now let's see, what's the next thing that I do? Yeah. So now the next thing I do is I'm going to start to combine terms here, okay? So I can't combine anything here. I'm going to skip this for right now and just go here to my quadratic term, or the one with two x's, right? So I can simplify this guy into this guy, right? So I've just combined the covariance matrices here. Okay, so I get this. Okay, and then for all of this, you can tell that I've taken the terms that have an xt out front, right? So I have an xt this guy, and I have an xt this guy, and I've taken those covariance matrices and put them together. And then the ones with an x on the back end, again in linear algebra, the order of these things matters. And so then I clump those together. Okay. So now what I am claiming is that this expression right here can be converted into a form like that. Okay, and so we're going to go through that here. So now AK is this guy, right? And the way I can identify that is AK has no dependence on x, and you look at all of the terms here, and there's no dependence on x. Okay. And then the sum of the coefficient b times x is equal to this, okay, which is this, Okay, now notice that I haven't given you b yet. I'm gonna that takes a little bit of work here, but for right now, just take it that that the sum of the b coefficients times x times the x's is equal to that whole middle term, and then we're going to find the b here in a minute, and then we have that the sum of the c coefficients times the x is equal to this, right? It's equal to this last term. Oops, equal to this last term. Okay, and so so we remove the thing that depends on x here, which is just these coefficients, or I shouldn't say doesn't depend on x, but I take the covariance matrices and the 1/2, and because I have to multiply by the x and the x, then that means that all of this is my c coefficient. Okay, and so now that's my c coefficient. Okay, so so we have a and we have the c coefficient, right? There's our c coefficient, and now we have to figure out b, and b is a little bit weird because it's in this big long form here. Okay, it's like two terms. One of the terms where the xt is out front, and one where the x is on the back side of all of this. And so I'm going to jump to what bkj is. Okay, it's this right here. Okay, so that's the coefficient b. All right, and so now how do we get there, right? So how do we get from this guy all the way to just this? Okay, so so the way that I did it was first to realize that this expression, right, which is just this right here, and the second part, that, right, that, these are just scalars. Okay, so in other words, if I were to so if I combined this and this, I'm going to well, if I multiply this xt through all of this, I get a scalar value, which is just a single number. And I also get a scalar value here. And it turns out that the two scalars are the same. Okay? They're the same value. So in other words, that means that this expression is equal to a couple of things. One, it's equal to its own transpose, right? So I have that this is equal to its own transpose, right? So I've just put the little t there. And that's equal to the second term, which is equal to its own transpose. Okay, and so now so for this whole expression here, I have to have two terms. Okay, and I have to pick from here, and they're all equal. And so I'm going to pick two that make it convenient to work with. Okay, so so what I'm going to do is I'm going to pick two that where I can put an xt out front. Okay, so I'm going to pick this first one, and I'm going to pick this last one. Okay, now this last one, it has a transpose on it, and when I apply that transpose, I just get the first expression back. I just get the same thing, right? So this final expression transposed is just the first expression. Okay, so now, well, I'm showing that all here. So now, when I combine all that together, I have that this expression right here is equal to, so I'm taking out the x transpose from both, right? Because that's in common between the two terms. Okay, and then I simply have two of these guys, right? Because I just added them together, right? Because again, this guy and this guy are the same after I transpose it. Okay, so I have two of them, but now I'm multiplying all of that by 1/2, right? So because I have two, then I can remove the 1/2, and I get this, and so I get that bkj equals this. Okay, so anyway, I hope that was helpful. Again, I think that this was overly hard, and if I've made mistakes, somebody please tell me. But I think maybe the important parts here are just simply recognizing that we can convert these things into expressions like this. So anyway, okay, thanks.